First off, let's check. Is it working? Okay, the PA is working and everything else. All I really wanted him to say was, here's Wally. But anyway, we'll start with this. I want to talk about exploring outer space tonight. I want to talk about some things that students have asked me, that people in the public have asked me, and this sort of thing about space, and some misconceptions, some common misconceptions about space. I want to talk about a number of misconceptions. I want to talk about, first, I'll spend a fair amount of time talking about misconceptions about gravity. People don't really understand what gravity is and isn't. I want to talk a little bit about living in space, some of the things that happen on orbit, some of the things that are totally unexpected, and this sort of thing. I want to talk a little bit, not a lot, but a little bit about rockets, how they work, how they don't work. I want to talk a little bit about atmospheric entry, what happens when the shuttle re-enters or when a spacecraft re-enters. I want to talk about space solar power. There are some great misconceptions about space solar power. It is not the be-all and end-all, and you'll see why in a few minutes. Other things I want to talk about, I want to talk a little bit about costs and benefits of space exploration. If I didn't talk about costs, everybody worries about the money that NASA's spending and this sort of thing. We'll talk about that. I want to talk a little bit about Spaceship One implications, what is and isn't going to be implied by Spaceship One. Then down at the end, I'm going to talk a little bit about Star Trek, some of the things we see on Star Trek. And then I'm going to talk about some space myths. I'll spend about 2 minutes or a minute and a half or something talking about aliens and things like that. That's where we're going tonight. Anybody want to leave? Okay. Let's go ahead. First, let's talk about gravity. There are a number of things about gravity that we're going to talk about. I want to talk about first the idea of shooting down satellites. Okay? I want to talk about, let's see if I can find the right button. I want to talk about falling into the sun. I want to talk about satellites hovering over cities like you see in some science fiction. Anybody ever read a science fiction in which a satellite hovers over a city? Yeah. No, it hovers over a city? Yeah. I want to talk about dropping bombs from satellites. Don't work, but we'll get there in a minute. Weightlessness, zero gravity, free fall, whatever the right terms are and wrong terms, we'll talk about that. We'll talk about escaping Earth's gravity, whatever that means and whatever that doesn't mean. And I'll talk about the zero gravity rooms down at NASA. Okay? They're not there, okay? Okay. Okay, first off, fiction. Satellites would fall to Earth if we shot them down. Now, this is a very nice picture and this sort of thing. The next one's an engineer's drawing. Okay? We shoot a satellite down. The parts, the missile comes up here, hits the satellite was coming along there, and we just create a lot of space debris. The debris, most of it stays in orbit. Sooner or later it might come down, parts of it would come down, but we create a lot more debris which is going to hit the shuttle or hit a spacecraft and this sort of thing. It's not a good idea to try to shoot a satellite down. If you want to take a satellite out, what you take is 2 cans of paint. If it's black, paint it white. If it's white, paint it black. You've destroyed the optics in either case, and in one case you fry it, in the other case you freeze it to death. Okay, dropping bombs from the satellites. Satellites are good bomb platforms. Others could drop bombs on us from satellites. Well, if you're in a satellite and you take the bomb, open the bomb bay door and drop it, what does it do? It floats right along with you. If you slow it down a little bit, what does it do? Well, it goes down and gets a little ahead of you because it's going into a lower orbit. It gets a little ahead of you, and it may well hit the Earth halfway around or a third of the way around the Earth. You can't see where you're bombing. You're lucky to hit the right state. Okay? It would fly along with a satellite and this sort of thing. Now, let's talk about falling into the sun. If we're not careful, a spacecraft could fall into the sun. It doesn't work that way. It doesn't work that way at all. It's really hard to fall into the sun. In fact, it's much easier to escape from the solar system totally than to fall into the sun. Look at my numbers, 48,000 miles per hour to get from, or you're already in low Earth orbit, to get to where you can at least graze the sun and maybe have it vaporize you. To get out of the solar system, it only takes 19,000 miles per hour from that low Earth orbit, but it took you 20,800, almost 21,000 miles per hour to get to that Earth orbit from the surface of the Earth. Mother Nature almost trapped us on this planet. If our chemistry was a little different, we didn't have quite as much energy in our rocket fuels, we would be trapped on this planet. But we can use staged rockets and this sort of thing to get up and out of there. If you look at that number, some of you may have heard the number 17,500 miles an hour. That's orbital speed. Where did the rest of that speed go? Drag. You had to push your way up through the atmosphere, and you're raising your height, so that takes some energy out also. Now, another fiction, satellites hovering over cities. Some science fiction things put a satellite directly over New York City, or one over Moscow, or one over Rio de Janeiro, or wherever. Satellites can only hover over points on the equator. What happens really is this. The satellite is basically in orbit around the Earth. The equator is there. The satellite is in this plane. The satellites move in an orbit plane. The plane contains the center of the Earth, so if I'm in an inclined orbit, I go as far north and as far south as I go north. So if I'm on the equator, I can stay around there, and if I get the right distance out and put myself in a circular orbit, then it takes me the right amount of time to go around, the same amount of time as the point under me goes around. How long is that? 23 hours, 56 minutes, and 4 seconds. Not 24 hours. Why? Well, basically because the Earth is moving around the Sun, and 24 hours is the time from noon to noon. And Earth, there are 360 degrees around a circle. There are 365 days in a year. Sort of gives you an idea where those numbers might have come from. So basically the Earth has to turn 361 degrees approximately from noon to noon. So that's where that extra 3 minutes and 56 seconds went, was in turning that extra degree. So it gives you an idea how rapidly the Earth turns. Now, let's look at the terms weightlessness, zero gravity, and free fall. Two of them are wrong. Weightlessness is wrong. These people are not weightless. Zero gravity is wrong. There is gravity acting on these people. Free fall, yes, they are in free fall. These happen to be 3 girls. They're in the Aerospace Engineering Department, 3 seniors in the Aerospace Engineering Department here at UT Austin, flying in a thing called, that we'll talk about in a minute, NASA calls this thing the Vomit Comet, the KC-135. You fly on it without a certain drug that they take called Scopedex. It's a mixture of scopolamine, truth serum, and dexedrine, and it keeps you from getting sick. If you don't take it, probably 2/3 of the people that fly and don't take it do get sick. And I mean, they get violently ill. We'll come back and talk about that in a minute, and people getting ill on this thing. Zero gravity or weightlessness. The fiction is, in orbit there is zero gravity. Things and people are weightless. Now, what does Newton's law say? If there's no force acting on a body, what happens? You move constant speed in a straight line, right? Okay? Another engineer's drawing. I'm in orbit. Gravity's turned off. I go off in a straight line, and everybody is lost in space. Okay? Now, what's really happening is that you're moving fast enough here that basically you move forward a foot and fall. Let's suppose your path bends and you fall down a foot. The Earth underneath you has dropped a foot. So you're falling around the world. And you continue to fall and fall and fall around the world. And that's what an orbit is. It's falling around the world. Okay? Now, we can get other orbits. Other orbits have shapes that are not circles. They're ellipses and this sort of thing. But as long as we stay close enough and at slow enough speeds, we will stay in orbit around the Earth or around some other body. But basically, you're falling, you're in free fall. That's the right term. Weightlessness, no. ZeroG, no. NASA uses both of the wrong terms. Okay? We'll see that in a minute. Okay? Now, escaping Earth's gravity. In orbit, we've escaped Earth's gravity. Obviously, from what I just said, we have not escaped Earth's gravity. We're still there. We're falling around the Earth. The Earth is acting on us. We don't want to get lost in space. Okay? Now, in fact, there is gravity in orbit, but however, if we get far enough away from the Earth, the gravity of the Sun dominates. If I get close enough to Jupiter, Jupiter's gravity dominates. And the gravity of the Earth, although it's still acting on us, and if I go twice as far away, its effect is a fourth of what it was. It's called the inverse square law, but every time you go double your distance, the effect goes down by a factor of a fourth, and you get away pretty far, and it's way down real quick. But if we're around Jupiter or the Sun or something like this, their gravity dominates, and we can forget the gravity of the Earth acting on us in orbit around Jupiter, for example. Now, another fiction. There's a room at NASA where the astronauts can go to experience zero gravity. Okay? I had a student from UT Austin, an engineering student, I will not give you his name, he was a he, that came and asked me about that room 3 weeks ago. Is there a room? He was a freshman. He can be forgiven, he was a freshman. But where is the room at NASA, and have I ever been in the room, and can civilians get in there? No, I've never been in the room, and civilians can't get in there because there's no such room. We'll see why. Basically, zero gravity is free fall. We can free fall for seconds off of a diving board, for minutes in Spaceship 1, but never standing alone like I am here on Earth. Basically, what's happening to us when you're standing here is the following. Here we have a Japanese astronaut getting the suit on, and basically what's happening, the forces acting on him while he's just standing there are the weight and the floor. The floor is pushing up on him, the weight is pushing down, and what you really feel for gravity is the combination of those things working on you. Now, and if he starts to move, he starts to walk, and he wants to walk that way over to the right over there, the friction has to push him, and as I walk across the floor, friction actually is what allows me to walk. If you've ever tried to walk on ice, you know. Because that's, you try to walk on ice and your feet just slide out from under you. There is a force when I try to walk across the room, and the force is in the direction that I'm trying to move. Now, what's happening in orbit is the following. Here's the astronaut. This is astronaut Bruce McCandless flying a thing called the Manned Maneuvering Unit, the MMU. He's free of Shuttle. He's very near Shuttle. The picture was taken from the Shuttle. But basically, the force acting on him is this. And why doesn't he fall? It's because he's moving in some direction. I can't tell from the picture which direction. It's some direction. He's moving at 17,500 miles an hour. Flying formation with the Shuttle. They're flying side by side but not touching. They're flying formation, and he's in orbit. And he's in a little spacecraft. This is a backpack with an air system and a pressurization system, and he has thrusters on board and a nice little camera up here. There's a lot of things going on there. He's flying. That's actually probably the smallest spacecraft the U.S. has built, right there. Okay, now, NASA does have ZeroG simulations, and they call them ZeroG, wrong term, but that's what they call them. This one actually does free fall. You do some free fall in there. That's the Vomit Comet. This thing is pulled up. We'll see the way it works. Then they have another facility called the Neutral Buoyancy Laboratory, and we'll talk more about that. It's a swimming pool. We'll talk a little bit about what they do there and what they do with the astronauts in there. Now, the KC-135, what happens is this, and you see this is a NASA chart, and there's the word ZeroG there. What happens is the aircraft pulls up, and when it pulls up, you feel like you weigh. The floor pushes up with you to make you do the turn, to pull yourself up. You feel like you weigh, what, 1.8 times what you normally weigh. Anybody that's ever ridden a roller coaster knows what the feeling is at the bottom of the hill when you're pulling up. You feel heavy. Now, going across the top, you know that you feel lighter at the top of the roller coaster. Well, they just make the top a little sharper, and you actually float. You know, it's what you always fear doing on the roller coaster is floating out of the seat. Well, that's what you do up here for 25 seconds. For 25 seconds. That's what those girls were doing in that picture. They were floating freely for 25 seconds, and then came this smash down to the floor, and you weigh 1.8 times what you normally weigh while they pull up, and then you go do it again. Well, what happened? One of the experiments that happened, one of the things that happened, I've heard this from several people. I'm not for sure that it's true, but I know that in 1980 the gymnastics team didn't get to go to Russia because we didn't go to the Olympics that year. We boycotted the Olympics. The U.S. gymnastics team volunteered to help NASA understand free fall, not ZeroG, help them understand free fall, so they volunteered to ride on the Vomit Comet. To make the long story short, never have there been sicker people. They couldn't get them out of the seats. They just belted them in, put a barf bag in front of them, and let them. And the story is, if you think about it a minute, here you're the most highly attuned people to knowing where down is in the whole of the U.S. and probably in the whole world. Your down is what you've trained to know where it is, and they take it away from you. You get very sick. Okay? Now, let's talk about the other simulation. The Neutral Buoyancy Laboratory at NASA Johnson is basically a swimming pool, a huge swimming pool. We'll see how big it is in a minute. Here you have, this is a set of side rails. This little area that they're working on right there is basically a simulation of the payload bay of the Space Shuttle. Here you have astronauts going along handrails, and what they've done with these astronauts is they have taken them, put them in the water, and have balanced them to where they're neutrally buoyant, where they don't float up to the top, they don't go down to the bottom, they're neutrally buoyant. If you look at the astronauts there's a bunch of weights on the legs. If you just put weights on the legs, the astronaut would always float head up. If you put weights on the head, they'd always float head down. They have to balance the astronauts so they don't turn over and twist and one side goes high. But they balance the astronauts, they feed them air through these hoses, and if they move slowly enough, and they move about the same rate they move in space, the water doesn't exert significant forces on you, and basically then you can use this as a simulation of doing work outside the space shuttle, outside the space station, or whatever. Now this is a photograph of part of the pool. I have a better diagram of that back here. The diagram is this. This is the Neutral Buoyancy Laboratory. This is a picture, this is a sketch of Space Station. Now the lab is, the Neutral Buoyancy Laboratory, the swimming pool, is not big enough to contain Space Station. Well, Space Station's huge. What they had to do was break it right here and right here. This is the central core section there. They broke it right there, don't have the rest of it sticking back. And then these parts back here are bent and are stuck along this side, and there's just another section of it. Down here at the bottom you see that section of the shuttle payload bay that was there. And this pool is 40 feet deep. Now, 20 feet of it's below ground level, 20 feet of it's above ground level, and down here in one of the ends, and I'm not sure which end it's in, there is a door. It goes into an airlock, so that if somebody gets the bins, you can take them out through the airlock into a pressurized chamber. They can put them then into a pressurized tank, pressurize the tank, move the tank into an ambulance that's right there, and take them to a hospital without having to ever get them above the water and out of the water and let the bins really hurt them a lot. Now, to give you an idea how big this thing is, it's 102 feet wide, 202 feet long, 40 feet deep, and it has 6.2 million gallons of water. You've seen these million-gallon water tanks? That's 6 of them, okay? Almost 50 million pounds of water in that thing. It's a huge, huge facility. Now, let's now go to living in space. Living in space, if you live in space, we all know space is a hostile environment. Unexpected things happen with motions, pressure, sound, other things. Let's talk about that. Fiction, Earthbound Intuition, about how you move around helps you in space. Well, it's not really true. There are a lot of things that happen in space that you really don't expect. Orbit removes the normal force, the forces supporting me. It removes the friction forces unless I go against the wall and shove off against the wall. I get a little friction then. But it removes most of those things. And there are some strange effects. Okay, first off, this doesn't seem like it has anything to do with it, but it has a lot to do with it. If you lose something in a spacecraft, you have little hope in finding it. Like if I set this thing out here in a spacecraft and it floated away, I wouldn't have any hope of finding it because it could drift anywhere. Wrong. You always look for it in the same place. Wouldn't that be nice if you had a place where anything that was lost, you looked for it at home and it was always in the same place? Where is that place? It's on the intake of the air circulation system. It always goes to the intake on the air duct. Okay? Be great to have that at home. Okay, now, problems with moving in orbit. I want to talk about something that I worked on in I think it's 1966, 67. Forgotten which year it was. This was Gemini 9. This was astronaut Gene Cernan. His goal was to come out here, come back to this thing, reach, put his left hand there, his right hand over here, his feet on that rail, and then thread some straps around, and then turn around and put this backpack on like is shown right here with those straps there, and then fly the backpack. It never happened. He got over there, he put his hands there, he put his hand there, put his feet there, and then he let go of this hand, and when he let go of this hand, he rotated about his left hand and rotated back up in a way where his head was here, his other hand was sticking out here, and he was holding on there, his feet were off the thing. And what was happening was the following. His air comes out through that hose right there, and down at the bottom, he breathed the air and then it would get exhausted. At the bottom of that box in front of him was a jet. Produced, I think it was 0.2 pounds of thrust if there wasn't a plate there to make the thrust multidirectional and no thrust at all. Right there, that dot right there is a sweat boiler. As he perspired, the sweat would boil off and it would produce 0.08 pounds of thrust if the plate were not there. Well, it took about 2 weeks down at NASA Johnson to figure out that the plates weren't there. They were on some guy's desk in Houston when these guys were in orbit, and we did a simulation, and sure enough, it rolled him up just exactly the same way that he was expecting to be rolled up. Now, there was another thing that's a little bit simpler that was happening. This is the cockpit of Gemini. That's where Tom Stafford was sitting over there. Gene Cernan was standing in the cockpit, or standing up on the seat there, I guess sort of standing, kind of floating, and he had a camera right here in his hands. He would take the camera, mess with it, get it all set, raise it to take a picture of the stars, and every time he would raise it to take a picture of the stars, he would float out of the spacecraft, and so Tom Stafford would have to pull him back down in. And they were wondering what was going on. Well, what was happening was that he would raise the camera, which would force his center of mass down into the springs or into the seat. I don't think the seat had springs, it was just cushions, but it would compress the cushions, which would kick him out of the spacecraft. We don't think about that. If you pick up a camera and raise it up, you're not going to float. It doesn't happen here, but your intuition doesn't work the same in space, okay? Now, this is a neat one. There's no air convection in orbit. Hot air doesn't rise. It doesn't know where rise is. Rise is any direction. Hot air is just going to stay wherever hot air is. Fiction is fires burn well in orbit. Combustion gases will actually put the fires out. You light a match, it'll burn for a second or two, burn all the oxygen around it, and then it'll go out. Well, this has a very, very, very interesting and kind of dangerous consequence. Don't sleep in an unventilated area. What happens to you? You run out of air, you run out of oxygen, you get this bubble of carbon dioxide around your head, and you die. It's, you know, it's not a real tough thing. Just don't sleep there. You're gonna die. Okay, pressure. If the spacesuit fails, the astronaut explodes. Did anybody see the movie Outland? Outland. They had a guy basically in an airlock, and the airlock depressurized, and they scraped him off the walls. It like ketchup all over the walls. Okay? That doesn't happen. Okay? Air, in fact, you get the bends, the air does leave the lungs, you get suffocation, there are no bulging eyes. Where's this picture from? Total Recall. You don't get that. Okay? You don't get the Total Recall situation. You know, Arnold doesn't end up looking like that if we take all his air away. He does die, but he doesn't look like that, okay? No exploding eyes. Now, let's talk about sound. Let's talk about sound just a minute. Sounds in space. Sound comes from molecular collisions. Collisions form pressure waves. The waves of molecules strike our eardrums. We detect the impacts with the mechanisms in our inner ears. A biologist would explain it a little better, but I'm an engineer, so I'll go with that. Okay? Fiction. There are no sounds in space. The fact is, space is not empty. There's a molecule here, and a molecule here, and a molecule over here, and sooner or later they hit each other. In the big scale of things, there are pressure waves in space. The astronomers have detected this very low B, they say it's a low B note. Basically, molecular collisions do occur. There is a sound. We can't hear it. We wouldn't even hear it if we could take our spacesuits off. Of course, then we would die like Arnold did. But one molecule hitting my ear and then another molecule hitting my ear really wouldn't work. Okay, I wouldn't hear that. Well, if we look at it, we think we could hear. Maybe we could hear on Mars because there is an atmosphere. Okay. Oh, gee whiz. Okay. Really, what happens is, see if this thing will go. Yeah. We must wear Mars suits, which sort of makes it where we can't hear very well. Our ears alone won't work, even if we were outside and could get outside the spacesuits, and we don't want to die. Mars' atmosphere, by the way, is mainly carbon dioxide, and it's like Earth at 100,000 feet. That pressure and density combination there is close to what it is. Of course, you can't live up there anyway at 100,000 feet. But if we had microphones and amplifiers properly built, we could talk, and the microphone could send it out into the Mars atmosphere. Another one could pick it up, and we could talk to each other. Okay? Now, rockets. Rockets push against the air, and rockets must thrust to stay up. Well, this isn't true. Rockets work better in a vacuum. They work by ejecting mass. And you throw something this way, you get thrown that way. If you don't think that, throw a medicine ball. Okay? Or catch a medicine ball, and you look at just the opposite. They work by ejecting mass, and once you get up to orbit, we've already talked about the fact you can coast. Atmospheric entry. On atmospheric entry, we talk about air friction heating the shuttle and causes the entry fireball. Well, the entry fireball, most of the heat does not go to the shuttle. Most of the heat stays away from the shuttle, thank goodness, or it would burn up. There's just far too much heat to be dissipated for the shuttle to take it all. Most of the air goes right there into the plasma trail. It basically tears the molecules of the air, tears the electrons off the molecules of the air. You get a plasma trail just like the inside of a neon light. And basically, you get this thing, and if any of you have ever seen the shuttle enter at night, any of you see it, it goes from horizon to horizon with this plasma trail, and it takes it a long time to fade. That's where most of the energy from the reentry went. Okay, now, this is a big one. Space solar power. An array of solar power satellites could supply Earth's electrical power. Okay? Now, let's talk about that a minute. In fact, the technology does exist. The size and mass required are prohibitive. Let's talk about how big it is and what it's required. These are some of the concepts. This basically is a set of solar power satellites. These things are probably a half a kilometer across or so. And it's a long gravity gradient stabilized thing pointing down at the Earth with a transmitter on the bottom. Here's a different design that's transmitting down to a receiving farm, which this is far too complex for the receiving farm. All you would need is a set of wires out across a field that the farmer is farming underneath. You know, it's a pole every half kilometer or something like that. And then there's electricity going to the city. Theoretically, this could work. Okay? But let's talk about it. U.S. power, currently we use about 6 kilowatts continuous per person. You want to know how many kilowatt hours? Multiply that by the number of hours in a year. In Europe, they use about half as much as we use. Our projected Earth population in 2050, between 8 and 10 billion people. And we assume that by that time we've gotten smart and we can use an average of 3 kilowatts per person. But the problem is that everybody on the Earth wants to use the power. Everybody, currently right now, 10% of the people use about 90% of the power. So we have the rest of the Earth out there trying to use their share of the power. They want computers too and places, and they want to use the same kind of things, the same standard of life that we have. Now, if we look at the satellite at Earth's distance from the Sun, you get about 1.3 kilowatts of energy getting on every square meter. We get about 20% of that down to the Earth. So if we do all the calculations, how big is the array? Now, it wouldn't be on one satellite, it'll be on a bunch of satellites, but how big is it going to be? That size. Okay, that's the state of Arkansas. Okay, now if we build these satellites and we say, well, okay, we're going to try to put that up there, and we build these satellites out of the lightest material we know how to do it, and we get real smart so they'll stay oriented without any additional mass and this sort of thing, what does it take? Well, currently we have a big rocket. It's a Titan 4B. It would take one Titan 4B launch per day, every day, with no system failures for 4,000 years. This is definitely not the solution. Okay? Now, what are we going to do? Well, we're going to use a combination of all sorts of things to get the power we need. Okay? Now, let's talk about costs of the space program. Fiction, it's a fiction that NASA's space expenditures are our primary national expenditure on space. The truth is that two other space agencies we don't hear a lot about, the military and the National Reconnaissance Office, these things each spend about the same amount that NASA does on space. We don't hear much about their successes or their failures because most of their programs, at least this one, were totally in the black for many years. That means not in the black and not in the sense that they're making money, but in the sense that if they tell you about it, they have to kill you. Anyway, that's one of the myths about the space program. The other fiction is NASA's space expenditures are large compared to other federal programs. Well, I wanted to go back far enough that we weren't worried about war in Iraq and Afghanistan and this sort of thing. In 2001, NASA's budget was 0.69% of the federal budget. Okay, less than 1%. Now it's a lot smaller even than that because NASA's budget hasn't grown and the federal budget has grown a lot. So basically it's probably less than 0.5% of the federal budget, maybe even smaller than that. Now, benefits of the space program. Okay. Hanging Velcro. Typical civil benefits of the space program. Wrong. Substantial civil benefits. Satellite communications. Satellite phones, TV, watching the Olympics in Greece from Austin, Texas, things like that. Enhanced medical diagnostics and monitoring. What happens there is that NASA had to be able to monitor astronauts on orbit flying at 17,000 miles an hour around the Earth from Houston. You know, if you can do that, you can monitor the patient walking down the hall in the hospital, going down to the cafeteria. That's not difficult at all. However, if you looked at one benefit of the space program, the one spin-off from the space program that was kind of the biggest, what would it be? It would be the descendant of the Apollo guidance computer. It's your microcomputer. How many of you used a computer today? Yeah, how many of you didn't? 2 or 3 of us didn't. But basically, that's the primary legacy of the Apollo program, is the microcomputer. Now, sure, we would have done it later and this sort of thing, but Apollo had to have something very lightweight that could do a lot of calculations. If we looked at what the Apollo guidance computer could do today, we would laugh. You know, it's like Bill Gates in 1979 says 640K should be enough memory for anybody. It's the same thing, you know. You can't predict. Okay, now, commercial space travel. Spaceship One won the Ansari XPrize on October the 4th, and a bunch of you went out and saw the XPrize display out there, and I think it's very nice that they were here. There were some things that came out in the press right after that. But first I'd like to, and we'll talk about that in a minute, but first I'd like to compare the Space Shuttle, which is not a very good vehicle, by the way. It's the best we knew how to build at that time, but it's compromised by budget restrictions and this sort of thing. It weighs 200,000 pounds dry. That means all the fuel's gone and everything else. You're not counting the weight of the booster and all that other stuff, which was 4 million pounds when it was on the pad. It goes 17,500 miles an hour, about 385 miles high. Those are just round figures that are sort of in the ballpark that it does. The Spaceship One was 6,800 pounds dry, a lot smaller, 2,300 miles per hour, and it flew 69.5 miles high. A tremendous accomplishment. But yet, on the other hand, it can't do what this one does. And I wouldn't want to fly something that small to orbit because I'd run out of air real quick, and then when I re-entered, I'd probably burn up because there's no heat shield. Now, fiction. This was one of the things that said that I heard on the radio. Now that civilians have gone into space, civilian flights around the moon and back to Earth are only a few years away. Not so. If you look at the energies involved, the energy to do an up and down flight like that of Spaceship 1 is much smaller than that required to go into orbit of the moon. These are rough figures, but basically Spaceship 1 went to about a little over 100 kilometers altitude. To put it into orbit, which we don't want to do, by the way, because I don't want to die, 85 times as much energy. To take Spaceship 1 to the moon, 150 times the amount of energy it took there. Now think about 150 times the boost of the rocket on the back end of that thing. It looks very, very, very different when we get there. Now also you want to carry all the food, all the air and the re-entry tiles and all the other stuff too. They're completely different designs. Now, let's talk about Star Trek. Okay? Okay. Talk about... Oh, wait till he gets through flying there. Okay. First off, fiction. By 2500, we will regularly travel faster than light at warp speeds. What's wrong? What is warp 10? It's 100 times the speed of light. You square the warp number and you get 100. At 100 times the speed of light, most of the... Okay. Now, what happens basically is that at warp speeds, first off, we don't have the energy source. They use these little dilithium crystals. I wish we had some. We haven't found them yet. And the flight times to the stars are still too long. You go 100 times the speed of light, and there are only a few stars you can get to in a reasonable amount of time, even at 100 times the speed of light. And that's warp 10. And the most I've heard them do is warp 11. You know, and that's really stressing the spacecraft and the warp drives and this sort of thing at warp 11. Of course, then that says we can't find a wormhole. I always wonder about the wormhole, what the worm's going to look like coming out of the wormhole. Okay. Other things. We have the tricorder. Medicaltricorder. Okay, it detects all anomalies without intruding into the body. Well, all I can really say about that is, wouldn't it be nice? No more probes, no more biopsies, no more this, that, and the other, all the things we have to look at and this sort of thing. That's another one of the things. But, you know, this one, we might, you know, we get better and better with this sort of thing. MRIs and this sort of thing are in that right direction. Okay, let's look at this one. This is basically the transporter. Now, what about the transporter? Okay? First off, there are major technical problems. It's a revolutionary if we can solve them. One of the major technical problems, you take the human being here and you say, I want a device that can store information about the state of every atom in the human body so I can take it apart and reassemble it somewhere else. Computers do not exist of that size. All the computers in the world are not that size. Okay? So we need lots of computing power, a lot more than we currently have. And then, if we could do that, what else could we do? Well, let's suppose you had a tumor in your head. Well, they beam you to somewhere else, and they take the tumor out as they beam you. So you arrive with no tumor. Great thing. But don't look for it tomorrow. Don't look for it the next day. Okay? Finally, we get down to our common space myths, and I'm running just about on time here. One of the myths is we never went to the moon. Okay? There are people that say it was all filmed in Arizona and this sort of thing. We actually went there. We can actually have taken pictures of things that are landed on the moon. We've taken photographs of the things there, and they say it's all fake, but it's not. It's all real. What about UFOs? Anybody ever seen a UFO? I have. Saw one flying across the sky today. I didn't know what it was. It's a UFO. Probably was an airliner, but I'm not sure. It was just going across the sky. Anyway, a good myth, Roswell, New Mexico is the site of an alien spacecraft crash. Oh, Roswell, there's a museum there. I know there's a museum there, but Roswell's really not an alien spacecraft. The thing that really tells me that all of this stuff is not very true is the fact that when the aliens abduct somebody, they go into the back hills of Tennessee or Transylvania, or get somebody with a big bouffant hairdo, missing 4 teeth, and they take them as a representative of the human race. If they're smart enough to know that they can look at our cities and this sort of thing, they wouldn't pick somebody like that. That's a little, basically it'd pick somebody who was educated and try to find out what we know and what we don't know. Okay, now, then at this point, that's us. We've done it. Thank you very much. All right. Any questions? Did I time it right?
Oh, we have time for questions, sure.
Yeah. Okay. Okay, questions, anybody? I'll try to answer your questions, but I reserve the right to say I don't know. Okay?
Okay, before we start the questions, please be as quiet as you can if you must leave so that we can hear the questions. Thank you very much.
You started to allude to this kind of went on. Why is it when people are working on the space shuttle and various other things, they appear to move slow? What makes you do that?
Repeat the question.
Okay. His question was why, when they're working on the space shuttle, they want to work slowly. They work slowly. Number one, they're working in a spacesuit. Okay. If you think about a spacesuit, and one of the problems with a spacesuit is that they don't have what they call constant volume joints. And if you just relax, you become Michelin Man. Okay? So you're always fighting against the suit. The second thing is that the area that astronauts have the most problem with is the gloves. And they come out of there, they'll come out of an EVA with the insides of their fingers rubbed raw from trying to grip things with those gloves. They use inner gloves and they'll use lubricant and this sort of thing, but still their hands, the glove is the hardest part. They work, and also they're working very slowly, because if you ever tried to put a small screw in, which they're trying to do, say like on Hubble, try to put a small screw in with 4 pairs of gloves on or 5 pairs of gloves on. It's rather difficult. You plan to do it very slowly. You move, so also you don't want to push off very hard and this sort of thing, because one of the things that people always talk about that I didn't put in here is a tether, and you get tethered. If you get a tether and you get a long tether out here and something goes wrong, the best thing you can do is cut the tether, because if you don't, you start wrapping up around the spacecraft and what's called conservation of angular momentum. You're very far out, you're moving slowly. You get closer in, you're moving faster and faster and faster, and then you break your helmet against the spacecraft and it's all over. Yes?
What's your position on a railgun shooting objects into space?
Railgun shooting objects into space. First thing, a railgun, the objects that a railgun shoots right now are, they shot a mass, it's probably a 1 kilogram mass, but a railgun shooting objects into space, you could do this. Number one, you and I are not going to ride that object. At 1,000,000 G's, you and I are not going to ride that object. We'd end up as a greasy spot in the seat. Okay? The second thing is, you could shoot something up there, but you really got to have something tough, unless it's water or food or something that you don't mind being squashed. But you could do it, but the problem is that the railgun, if you're firing from low down in the atmosphere, most of what you fired gets burned up before it gets out of the atmosphere. If you go to the top of the highest mountain, yeah. If you were on Mars using a railgun to put yourself in orbit around Mars, I'd go to the top of one of the 4 mountains on Mars that's 25 kilometers high, above 99% of the Martian atmosphere. Yeah, you could use a railgun. But then you better have another rocket on it, because it comes back around and hits the backside of the mountain. Sometime, yeah.
You gave us dry weights of Spaceship.
Yeah.
Is that, and then you gave us like the weight with all the stuff. Is that the heaviest thing on the Spaceship? the fuel?
The fuel, oh yes. If you're sitting on the pad and you're trying to launch yourself into Earth orbit, fully 90% or more of the mass that you've got is fuel. Okay? It's true on the Saturn, it's true on the Shuttle and everything else. You're going to use that all up in the first 8 minutes. And that's why Mother Nature was really tough with us, because if gravity, of course, if gravity had been less, we probably wouldn't have the atmosphere and we probably wouldn't all be here. So it's a trade-off there. But yes, it's 90% or more of what's sitting on the pad is fuel, is the oxidizer and the propellant. Yes, over here.
Could you speak to the proposed space elevator that you're talking about?
The space elevator. This is supposedly what this is. If you remember that geostationary orbit there that I had with the satellite hovering over the city, what they want to do is they want to build a tube, a long tube. I don't know how you deploy it as the first thing, but they want to build a long tube that goes from above geostationary orbit far enough that you could use the counterweight out there beyond it has to be beyond geostationary orbit to run a tube all the way down to the surface of the Earth. I think it's something on the order of 44,000 or 50,000, maybe 60,000 kilometers long. And they want to build it out of what they call carbon nanotubes, and it's got to be there without any flaws, because if it breaks, it's like having a writhing snake around the Earth, and it's going to take out cities or whatever. Even though it's only a tube yay big and this sort of thing, it's 60,000 kilometers long. Wrap all the way around the Earth. If you did it wrong. But the main thing is, how would you deploy it? Because you sort of go out to geostationary orbit and start putting this thing out, going both directions all at once. And it's very difficult. I can't even conceive of how you would deploy this thing, and what it's Once we got it there, sure, you could use it as a space elevator and go up and down. But as I tell my students, the carbon nanotubes that they're talking about right now, to me, they're still what I call unobtainium. You build a spacecraft out of the super material called unobtainium. And so, yes?
What are some of the things like, I know that a lot of geologists and geophysicists do things with Mars. What are some of the things that we can learn about Earth by studying rocks on Mars?
Learn about Earth about studying things on Mars. I'm not a geologist or a geophysicist. I'd almost hate to get into that. We learn things about Mars by studying rocks on Mars, but I'm not sure what we could learn about Earth. We do learn some things about Mars by studying meteorites that come from Mars that are found primarily down in the Antarctic. But I don't know what we could learn about Earth. We might, I don't know, I choose to say I don't know there, because it's one of these things. Maybe a geologist, is there a geologist or a geophysicist in the room that can answer that? Is that you, or are you just asking a question?
We might learn about what the Earth was like when there was much more CO2 in the atmosphere.
Okay, there you go. We've got one right here.
We also have a question from a bunch of questions from the internet. Let me read one of them here. This question comes from Stephen. With the current administration's push for the advancement of human space travel to the Moon and Mars, what advancements in technology must be made to achieve our goals?
Well, the biggest thing we need to do, in my opinion, and this is, I could be wrong, the biggest thing we need to do is to find a way to launch things more cheaply off the surface of the Earth into low Earth orbit. Because currently a shuttle is $10,000 a pound. Launching me, that's a lot of money to launch me into orbit, and I'm a little guy. I don't know what it is to launch a big guy. And it's not even anything that my spacesuit or my food or anything else. If we could get it down to $1,000 a pound or $100 a pound, that would be really good. That would be really good. But I think that's the main thing, is to find a way to get things to orbit much more cheaply. Okay, you want to take another one from here? Let's see. Yes, you back there.
How long do those rovers, like the Mars rovers, how long do those last, like, batteries and stuff?
How long the battery? Well, the batteries are recharged. They're still working. And they think, I heard a newscast the other day, one of them's having a little more trouble than the other one, but they think they'll last well into next year. They'll make a year. They landed in January last year. They think they'll make a year. It's all gravy from this point on, because they were meant to last, 90 days or something like that. They've gone a year. They may well be able to be, there's something, really what they expected to have happen was they expected dust to get on the solar panels, and one of them looks like a little whirlwind or something, dusted off the panels. Hey, great. Yes?
How long till the space station is completed?
Oh, boy. How long till the space station is completed? Well, they hope 2010 because that's when they want to fly the last shuttle mission. But the question is, will it fly that soon? Will it fly that often? What is completed? I think the space station is a national laboratory or an international laboratory. The question is, if it appears to be, if we complete it and then we quit flying the shuttle and we start flying other things up there, and it turns out that there's some really good science going on in the space station, it may not be completed for a long time because we may be building and adding things onto this thing. It's like, how long till the University of Texas is completed? So ever since I've been here, and I've been here since 1957, there's been this hole in the ground that they put a building in, the hole moves, they put a building in it, the hole moves, they put another building in it. Yes, back there. Are planets able to move out of orbit? No, they're always in some orbit. They're nudged by other planets and this sort of thing, but they will always, we hope, be in an orbit. Now, there are situations with 2 and 3 bodies and this sort of thing. If we had 2 or 3 stars orbiting each other, there is a condition in which one of them would get ejected from the constellation, and that sometimes happens, but it's not going to happen in our solar system, not in our lifetimes anyway.
There's a young boy who's been standing for a while.
Where?
Just gave up the ghost. Oh, wrong.
What was the question?
How long did it take to build the laboratory pool?
Oh, that pool? I don't know how long it took to build the wet F. I know it was under construction for a couple, 3 years. I don't know for sure. I wasn't there. I didn't go out there. It's on the backside of Ellington Field at NASA, but it's a huge pool. About 5 years. 5 years. About 5 years from a fellow that works down there. He says about 5 years it took. What they had to do, they actually dug this thing down 20 feet and they pumped groundwater out forever before they ever started doing anything else.
This guy's had his hand up for a long time.
Yeah.
If we did find microscopic life in Mars, how could we know that it didn't originate here in Earth and carried out by space rockets into Mars?
Well, first off, if we found life on Mars and it was something that we knew about here on Earth, that would be, would be a good suspect that we had carried it there. What if it was totally different? What if it was something that had never seen? That was just very likely. If there is life on Mars, it's not going to be like what it is here on the Earth.
What if it did evolutionize there?
Well, it would have to be pretty fast because we have not been sending things to Mars for very long. And the thing is, where we expect we'll find life is down below the surface, not where we've landed things on the surface. Yes?
Has there been a movement ever to bring back the Orion project?
Not that I know of, but things like that are still under consideration again.
Can you tell us about any of them?
No, I don't know really a lot about them right now. I just know that Orion and Nerva and this sort of thing have been talked about. And we look at all the options. Currently, NASA is looking at all the options for putting things back into orbit. Let's see.
Take another internet question. This comes from David. Is space tourism probable and can it be achieved?
Is space tourism probable and can it be achieved? I don't. Only if we get the low cost of orbit. If we get the cost of orbit down, can you achieve? If it gets down to $100 a pound, I'll probably try to go. At $1,000 a pound, I weigh too much. Unless of course, I get real rich, and that's not going to happen. Let's see. Go ahead.
You mentioned how the space shuttle is a less than ideal system.
Yeah.
What kind of improvements would you feel?
Well, number one, they're not going to improve it. It's going to just be flown out. But if you had to do the shuttle, first off, nobody at NASA wanted to go with solid rockets. They wanted to go with liquid fuel boosters on it. At that time, money was cut off, turned on and turned off by Congress at the wrong times or at the right times. So it was really money and schedule. The schedule probably was even a bigger driver than the money, in that they didn't have the time to make the launch deadlines and this sort of thing. They didn't have the time or the funds to do the research they needed to build reliable liquid fuel rockets for shuttles. So they went with solids. Solids are they were a known technology and this sort of thing at that time. Okay, yeah.
Have we found a new kind of liquid fuel that's going to give us the proportion a solid fuel would give?
Solids are only about 3/4 as good as a hydrogen oxygen. The specific impulse, which is a measure of the speed of the fuel, is only about 300. Hydrogen oxygen is about 400. There is a combination that's a little more energetic than hydrogen oxygen, but we don't want to use hydrogen fluorine, because hydrogen fluorine makes hydrofluoric acid, which sort of etches the windows all over Florida and things like that. This is not a good thing to do. It's rather nasty chemical.
We haven't gone to this section.
Okay.
Pick one of those.
There. When do we expect Hubble to fall? Heaven only knows, because Skylab came down several years before we thought it was going to, because we launched Skylab at a time we thought we were going into a sunspot minimum, which if there are a lot of sunspots, it makes the Earth's atmosphere expand, which gives you more drag high up. We thought we were going into a sunspot minimum, which has about an 11-year period. What happened was this minimum all of a sudden turned into a maximum, and so the atmosphere expanded, and it came down a lot earlier. Yes, back there in you in the aisle.
Okay. Have you ever been on the Vomit Comet? And if so, what was it like?
I've not been on the Vomit Comet. Is there someone in here that's been on it? Any one of the students here that's been on the Vomit Comet? Where's Amanda? She wasn't here. There. You been on the Vomit? No, you're raising your hand. No, I've not been on the Vomit Comet. I have done ZeroG in a T-38, but that's a little different because I was strapped in.
What was it like?
It didn't feel much different. It didn't feel much different. Of course, I wasn't floating freely. I was strapped in, so it's cheating. My camera felt that way. I didn't ask it what it felt like, but it felt that way. Yes, you in the back. Red shirt. Who and how did they determine, I think it was Michelson-Morley experiment, determine the speed of light in a vacuum. They actually did it with a rotating mirror system. I don't know, I've done the experiment in physics, but it's been so long ago. But they did it with a spinning mirror, and well, just look up in the physics book, Michelson-Morley experiment. Yeah.
More questions for Professor Fowler.
There's one back there, you.
Following up on the speed of light, do you think it's possible to travel beyond the speed of light?
Well, only Einstein said it wasn't. I'm not Einstein, so I'm not going to say yes or no. But currently, our current physics says it's not. Our current physics could be wrong, probably is somewhat wrong, but even the Newtonian stuff that they say is wrong at high speeds is, as we engineers say, close enough for government work at low speeds. We can get to the moon and back with Newtonian stuff. Yes?
Do you see us going back to the moon for a particular reason?
Yeah, I think going back to the moon is basically a thing that we're going to do, because if we go back to the moon, we can test a lot of the stuff that we're going to go to Mars by going to the moon, and it's not that far away. If you go to Mars, you're out there, and the standard missions to go to Mars are 3 years long. Okay, you go to Mars, it takes you about 270 days to get out, 259 days to get out there. if you do what they call a Hohmann transfer, which is the minimum energy transfer, you get out there and you wait for Mars to get back into position so that you can come back the minimum energy way. You're out there for about over 1,000 days, about 3 years. You can go to the moon and come back in what? 4 or 5 days? And that's if you don't go real fast. And you can go faster coming back home if you had to. Where? You. Yes.
What's the longest range of satellite since transmissions back to Earth?
Oh, gee, the longest range of satellite, I think one of the Voyagers is out there, and I don't know how far out it is now, but you can go to the Jet Propulsion Laboratory website, www.jpl.nasa.gov, and look up Voyager, and you can find out how far these things are. And the big ear, the big antenna out at Goldstone in California is a 70-meter across dish. Okay? Now, that's not nearly as big as the dish at Arecibo down in Puerto Rico, which is 300 meters across. But this one's steerable. It can point anywhere. It can track satellites across the sky and this sort of thing. And it can basically pick up a signal that's basically a billionth of a watt. Now, if you look at, you're transmitting out there with about 100 watts or 200 watts, and you start doing, every time you double the distance, you cut the signal strength by a factor of 4, and it can still pick it up. And it's, gee, I'm not sure. Anybody know how far the Voyager spacecraft are now? They're beyond some of the Pioneers. They've gotten further than that because they went out faster. But they're way far out there. Yes?
Is it hard for the astronauts to make the transition from space back to Earth?
Depends on how long they've been up there. If the astronauts have been up there a long time, it is a problem because there are medical things going on. Number one, you decalcify. It's like osteoporosis. You're losing calcium from your bone, the bones and this sort of thing, and the other thing, and the astronauts up on space station, for example, stay up a while, and if you stay up space station for several months and this sort of thing, you've got to exercise every day, or you probably won't even be able to kind of get up when you land. You might be able to stand up, but you might be dizzy, or your tendency to break bones and this sort of thing for several weeks or months until you get back. One of the things NASA is doing, for example, with medical research, they're looking for ways to measure bone decalcification for astronauts on orbit, and these things can be used to look at osteoporosis for people here on the Earth.
Another question from the internet. This question comes from Lindsay. Does our tax money fund space programs?
Yes, absolutely. Our tax money funds space programs, it funds poverty programs, it funds highways, it funds all sorts of things. But primarily it funds the national debt. Interest on the national debt, which is the big part of it. Yeah.
What stops Coca-Cola from putting up a billboard in outer space?
Cost. Coke can't afford it. Yet. I don't know if there's an international treaty on not advertising in space, but I don't think so. Might be a good idea, Yes.
Do you see any practical terraforming things that we should start doing fairly soon?
Terraforming on Mars or something like that? On the moon? I don't know. First thing we have to do on Mars, the moon I don't see very much that we can do. Number one, there's not any water there, or very little water at the poles. But on Mars, first thing we have to do is make sure, number one, the water is there. Number two, we're about 99.9% sure it's there. But the question is we have to figure ways to get it and then start using it. And you're not going to ever have a Mars that's like Earth, really, because the pressures, the gravity's not enough to hold a good atmosphere and this sort of thing. You can live very well in an enclosed habitat on Mars, but not outside. You got to put your spacesuit on and drive your Mars buggy, which can't have a gasoline engine in it because there's no oxygen in the air. So you have to carry your oxygen or whatever fuel you're using to drive around with you. There are some major problems, but they're overcomable. There are even plans to fly airplanes on Mars, but they're very, 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 very lightweight. They're not going to be Mars airliners, that's for sure. Boeing on Mars is not going to build airliners.
That guy's arm's about to fall off.
Yes, the guy in the back with the arm that's about to fall off.
Do you think there's any feasible way we could construct Orion elsewhere where the fallout wouldn't hurt life on Earth? Do you think it would be feasible?
I don't know. I really don't know. Don't know the answer to that. Nuclear rockets and this sort of thing are a major problem. There are great ecological problems with that. There are great political problems with that. There are all sorts of problems. We will take, going to Mars, once we go to Mars, we will take nuclear power plants to Mars. There is just no other way to do a Mars colony other than use nuclear power plants on Mars. There's not going to be a choice. We have to do that. Probably even on the moon, because if you're on the moon, for example, you've got this lunar day, which is 14 Earth days long, and the temperature outside can be 230 degrees Fahrenheit. You better have a good air conditioner. An air conditioner requires power. So you do that. Then you get this night when the temperature is 230 degrees below zero Fahrenheit, and you better have a good heater. Yes?
Well, since there wouldn't be as many people like on a terraforming colony, couldn't you run it on solar power?
Solar power is, first off, at Mars, you're only getting about 44% of the amount of solar energy because you're further out.
Well, then what about on the moon?
On the moon, yeah, but the thing about it is running anything on solar power is basically a it basically, number one, you have to take the solar collectors, and they're not as the energy density of a solar collector is much smaller than the energy density of a nuclear power plant. And if you want to go, how much power do I get for how much mass? You take the nuclear power plant.
So it's too expensive.
It's too expensive, yeah. Unless you build it. Now there have been some plans for building solar arrays on Mars, or on the moon rather, made out of lunar materials, which might be a good idea.
Okay. Maybe one last question, the gentleman with the arm over there.
Is there what? Echo. Echo. There is sound in space. I think these things could reflect. The sound waves could reflect, but they're so diffuse, I don't know what they would reflect from. They might reflect off of a planet, but I don't think we would be able to detect them. So there might be an echo in space, but I don't think even the astronomers who found the B flat could hear it.
At this point, I would not only like to have us thank Dr. Fowler, but all the people who made those wonderful exhibits that we enjoyed before the lecture. Thanks a lot.